Welcome to Study Loop.
In this problem, we're going to talk about the work energy theorem. So basically, let's say that a quantity uh, W of work is done on a system, then the increase in energy of that system is equal to the work that's done in the system. Also, we need to remember that the kinetic energy is equal to 1/2 of mv squared, while the gravitational potential energy is mgh, where h is the height of the particle and m is the mass. So what we have is a skier that has a mass of 62 kilograms, and she's moving with an initial speed of 6.5 meters per second in a frictionless ice surface. And then she starts to move in a rough patch that has a coefficient of kinetic friction 0.3 and has a length d of 4.2 meters. Then after that, she skis down a hill that has a height of um, 2.5 meters. So I'm just gonna draw her um, journey here. So this is the hill. This is the hill. Then we have the rough patch. This here is the height h, while this is the distance d. Okay, and our goal is to find what is the final speed vf of the skier. And in order to find this, I'm going to use conservation of energy. So first, notice that the change in energy is equal to the final energy minus the initial one. The final energy here, I'm going to use the zero of the potential energy to be in the ground, this point here, this bottom point here. So there is only kinetic energy. So the energy is 1/2 of mvf squared, while the initial energy is 1/2 of mv0 squared plus the gravitational potential energy, which is mgh. And we know this is equal to the work. And the work, notice that the work is done only by the friction force, and the work must be negative. It must take out energy from the system, because the friction force generally will make the system lose energy. So for that reason, the work will be negative. So it's minus the mu times the normal force, and the normal force must be just mg, actually times d, of course. So we have the delta E, that is 1/2 of mvf squared minus 1/2 of mv0 squared minus mgh is equal to minus mu mgd. The m's cancel out. So I'm going to isolate vf since that's what we want to find. So vf is the square root of v0 squared plus 2gh minus g mu d. 2g mu d, actually. So Vf is equal to the square root of V0, that's 6.5 meters per second, squared plus 2 times 9.8 meters per second squared times h, and h is equal to 2.5 meters, minus 2 times 9.8 times 0.3 times d, which is 4.2 meters. So Vf is equal to 8.16 meters per second. This is the final velocity. Now in question B, we have to find what was the internal energy that was generated when crossing the internal patch. Well, the internal energy was just the energy that was lost, that is, the work that was done on the system, basically taken away, the energy that was taken away from the system. So basically, what we have to calculate is minus the work to calculate the energy that was given to the system. And the minus is here because the work is negative, and the energy that was gained by the internal energy that was gained is positive. So it's just mg mu d. M is 62 kilograms, G is 9.8 meters per second squared, mu is zero point 0.3, while D is equal to 4.2 meters. So the internal energy increases by 766 joules. And this concludes our exercise.